Hello and welcome to Sigma Phi's Distinguished Lectureship Series. I'm Katie Burke, Digital Features Editor at American Scientist Magazine. I'm here today with Jim O'Connor, who's a research geologist at USGS. Hello, Jim.
Hi, Katie.
To ask questions, anybody who's watching this and joining us live can use the chat window through Adobe Connect. And you can also submit questions through Twitter using the hashtag AmSciTalks. That's AmSciTalks. Sigma Phi members can also join discussion about this talk after the fact using the Sigma Phi communities page. Okay, so Jim, just to get things started, you've been studying floods and dams for a long time, and you've done some really interesting work on some of the largest floods throughout history and ancient and geological times, whatever we can find out. I'm sure there's still much to find out about ancient floods and current floods, but what do we know so far about the largest floods that have occurred and what they're like?
Well, they're big.
And what is big? Like, how do you measure the largeness or the magnitude of a flood?
Well, there's a couple different ways you can think about flood size. One is just how much water was involved, just the total volume of water. Another way to think about it is how much water was involved at any one time. So that would be what we call the peak discharge of the flood. So that would be a rate of water movement. So some of the largest floods in Earth history have had peak discharges, flow rates of 10 to 20 million cubic meters per second.
And how big is that? Can you put that into perspective?
Yeah, so that is hard to put into any kind of into perspective. But for example, the largest flood that we know about was about 20 million cubic meters per second. It was one of the Ice Age Missoula floods that affected the Pacific Northwest. And that flood was probably about 400 or 500 times larger than any historic flood on the Columbia River.
Wow.
So several hundred feet deep, moving in places at 30, 40, 50 miles per hour. Some of the largest volumes, a lot of these really large floods happened during the end of the last ice age, when the glaciers were melting and there's a lot of water kind of around the edges of the ice sheets and in some of the big closed basins of the world.
And you wrote that large ice age floods could affect climate change in the way that they discharge to the ocean. Can you talk about that? Explain that?
Yeah, I'm not really an expert in the details of that, but what does happen is when you put all this fresh water into the oceans in certain key spots, like particularly in the North Atlantic, it affects the way that the ocean currents kind of move north and south, and it really changes the way the atmospheric heat is and ocean heat is moved around the globe, and that can trigger these really cold periods. And it's evidence that at the end of the last ice age, when we had some big floods into the North Atlantic, that it triggered episodes of pretty radical global cooling.
And so this idea that this particular flood that you talked about in the Pacific Northwest was this huge major event was once controversial, right? So can you tell me about how geologists figured that out, who first proposed it, and what the reaction was from the geological community?
Well, that's kind of one of the really interesting things about large floods. I mean, geology, the science of geology came of age in the mid 1800s, and in part, in part, its sort of coming of age was getting away from the idea of these Noachian biblical floods shaping the landscape. And so when this early geologist working in the Pacific Northwest, J. Harlan Bretz, proposed that instead of the landscape there being formed by slow, gradual processes, which was kind of the hallmark of how geologists thought about the world back then, that instead there was a big flood that shaped the landscape. It was that idea was pretty controversial, in part because geologists felt that was setting the science, going back to these big floods, calling upon these big floods to form a landscape, sort of going back. But in the end, Bretz was working on this in the 1920s for the most part. But by the 30s and 40s, he had amassed a fair bit of evidence, pretty compelling evidence that indeed it was a large flood, or as it turns out, several large floods that created that landscape.
And what was some of that evidence?
Some of the evidence that he called upon were just the fact that he had all these channels operating at once. Most rivers don't work that way. And then really what was compelling was when the first aerial photography became visible, and people could see these giant current ripples, these giant current dunes that they were so large you really couldn't appreciate them on the ground. You could see that there were these hills, but when you got up in the air, you could see that there were these patterns of like current ripples you see at the beach, or in small streams under, that are formed by rivers. But these current ripples were, had wavelengths of 100 feet and heights of 20 or 30 feet in places. So that really was the most compelling evidence.
And how does climate change and rising sea levels in turn affect when and where the geologic record, where and when in the geologic record we see major floods like this happen?
Well, for these really big floods, they seem like they happen at times when you have pretty big changes in the hydrologic system. Those can be sometimes when glaciers are advancing and they're blocking valleys and forming lakes, or they can be during warming periods, especially at the ends of ice ages, where you have a lot of meltwater being generated, and you still have drainage basins that aren't quite yet back together. They're in part covered by ice, and parts of them are blocked. And the ice itself will press down on the earth, and you'll have these moats of meltwater accumulate around the edges. And those moats of waters will sometimes breach divides and cause large floods. So it's these times of changes that really seem to be pretty important in at least generating the largest floods. But you can get pretty large floods even during times of relatively stable climates, in particular from landslides blocking valleys and lakes forming behind those, and then breaching.
And so that kind of can lead us into talking a little bit more about historic floods too, because the USGS has one of the longest term stream flow records in the world. If not, I don't know whether it is the longest, but it certainly is one of the few. What have you learned about the patterns of major floods and destructive floods from studying them?
Yeah, the gauge, the stream gauging record has really been helpful, over the course of more than 100 years now. USGS has been measuring stream flow from a total number of spots that it's upwards of 20,000. Right now, we're measuring stream flow at about 7,000 or 8,000 different places in across the country. And by looking at those records over long periods, we've started to see some patterns of where floods are bigger than others. And there's seems to be a couple really important ingredients that sort of set the stage for relatively large floods. One is, as you can imagine, places where there's a lot of rainfall, or rainfall comes down in a hurry. Those places can produce large floods. But the other important ingredient is topography. To have some sort of relief in the landscape, and that seems to have two effects. One is it increases the local rainfall, because you have atmospheric lifting, orographic lifting that increases rainfall. But also it allows the water that does land onto the ground. If it's steeper, it moves down faster and it concentrates faster, and that leads to bigger peak flows. You put those ingredients together, there's a few places in the U.S. that we think of as being flood hotspots. The tropical places like Puerto Rico and Hawaii, they both have relief. They're both at low latitudes where rainfall intensities can be really, really high. So those are pretty significant flood hotspots. The biggest flood hotspot in the 48 contiguous states is Texas, where you have a lot of moisture coming off the Gulf of Mexico, and that moisture intercepts the topography, particularly in central Texas, places like the Balcones Escarpment, and that combination has produced some of the really largest peak flows, at least in terms of relative to the area that's contributing to those flows. And in part because of that, Texas has really suffered the brunt of flood damage and flood fatalities particularly from flash floods.
Yeah. So have you ever experienced a flood? Have you ever experienced a flash flood? Do you have any field stories that you can share?
No, I've been pretty lucky in that I haven't been dangerously close to anything like that. I mean, I've been certainly in places where there have been large floods. I live in the Pacific Northwest, where the rivers do get up high, and I've seen some pretty good flows, but I've never really been in a situation where I've seen an immense flow or flood in action. I'm pretty lucky, though, in that I have, I've gone to places shortly after large floods and seen the aftermath. It doesn't take too much imagination to sort of picture in one's mind what the situation was like when the water was up.
Mm-hmm. So one of the things that you've also studied is is dam removals and dam breaks. So can you talk a little bit about some of the major dam breaks, what we've learned about that, and some of the major dam removals and what we learned from that? Those are just kind of two separate questions.
Yeah, well, they are. It's related, and
Uh-huh.
and sort of the relation there is I've always been interested in things in sort of these spectacular geologic events and these dam breach floods from dam breaches, whether they be constructed dams or natural dams. Are incredibly powerful, and they have been locally very important in shaping the landscape, and that's kind of what's triggered my interest in those. The dam removals are typically, I mean, we try to, managers try to avoid to have disasters associated with dam removals, but in certain situations, the removals have been pretty spectacular. Dams have been breached all at once, and you have this gush of water and sediment come out, and and the consequences can sometimes be pretty spectacular, and they also are pretty educational in terms of what happens to a landscape when you release a lot of water and sediment at once, and that happens with dam removals, but it happens with other types of geologic processes too, like landslides coming into a valley or volcanic eruptions. So those types of that's in part motivated looking at dam removals, but the other part of it is that dam removals are viewed as one means of restoring rivers, bringing back some of the particularly ecologic function of rivers that were changed by putting dams in. The Pacific Northwest, one of the major changes by putting a dam is that you, at least in not always, but in many cases, you block the migration of fish species, anadromous fish that would have gone upstream of these dams. And it's we're learning by looking at these dam removals how these systems respond. Do fish go back upstream? How do the habitats evolve in conjunction with the changed system? Does dam removal, essentially, does dam removal work as a way of restoring rivers? So that's been really one of the main questions that we've been looking at with these dam removals.
Uh-huh. And I would imagine that when you remove a dam, it's a kind of a huge disturbance at first. It's a big event, and then after that, you see some sort of succession or recovery. And how long does that take? And is it possible to see some resilience in the system?
Yeah, that's one thing it's been really fun. The first big dam removal that I worked on was about 10 years ago now, and it was really exciting. But what was amazing was the next morning that the dam was breached about 5 o'clock in the afternoon, and we were up there all night making measurements. But early the next morning, we could see fish moving upstream past where the dam was.
Uh-huh.
You can see kayakers coming down too. So it was you could just see the evidence of the reconnection of the system, and it does seem like it's happened with a lot of dam removals I've been involved with. It's happened very, very quickly. These rivers are resilient, they're nimble, and they do change pretty quickly. Of course, in most cases, they won't go back totally to what they were before the dams went in, because other things have happened in watersheds that affect how what the river corridors look like, and how it kind of limits their options in some cases to what they can go back to. But for many of the dam removals that we have worked on, it's amazing how quickly things have changed and how the ecosystems seem to respond.
And dam removals in the United States have increased in the past decades, correct?
Yeah, it's been a huge growth industry, and in large part it's motivated by river restoration issues, but perhaps the most important aspect or motivation is that there's so many old dams out there that are in many ways liabilities. There's safety issues. They're not serving any function.
What's unsafe about them?
Well, a lot of them, are built 100 years ago or even longer, particularly in the Northeast. The old, mill dams powering mills, and they're crumbling away. They're falling apart.
And so they have the risk of breaching, I guess.
They have the risk of breaching in an unplanned manner, or their safety issues for people just hanging around them, which oftentimes happens.
Mm-hmm. And so the dam removals are just motivated by wanting to mitigate those safety issues. A lot of times,
it's everyone is a little bit different. In the Northwest, where I'm at, where there's been quite a few fairly large dam removals. Most of them, not all of them, but many of them were hydropower facilities that were coming up for relicensing. Most of them were built in the 40s and 50s and 60s, and every 50 in their original licenses were for 50 years. And when they come up for relicensing, there's often conditions associated with those new licenses, like to implement fish passage or to mitigate for ecological consequences. And in some cases, it's just not worth it to the utilities to make those changes. It's cheaper for them in the long run to remove the dam. Although that calculus changes, could change in light of climate change, and how hydropower is viewed as a sort of low carbon energy source, and so it could be that that the equation evolves with time.
That energy becomes more valuable. It's not so much that the power that they could generate would change.
No, but that low carbon footprint energy becomes more attractive.
Right. And also dam building is up around the world, especially in Asia and South America and Africa. So that's introducing new hydrology and the potential for dam removals in the future, right?
Yeah, and one thing that we're hoping on by working on dam removals, and I mean, there's been a lot of work done over this last several decades on how putting in dams affects rivers. Much less work on how taking dams out affects rivers, but we're hoping that by better understanding dam removal, we can help improve the science of dam construction, and maybe dam placement could be done in ways that not just minimize the ecological consequences of putting that dam in, but looking, 50, 100 years down the road,
Mm-hmm.
how might things we do now make the removal process smoother in the future. Can't really predict exactly how that's going to play out yet, but it's something that we're trying to be mindful of in
Right.
renewable studies.
Have you visited any of the dams in some of these other countries yet?
No, no. Well, I've certainly seen dams in other countries, but it seems like I find enough stuff here in the Pacific Northwest to keep me busy.
Yeah,
Go
for sure.
to keep sort of a rich list of unfinished research projects going on.
Uh-huh. And so, as you've studied floods, I'm going to return some more to the historic, your study of historic floods over time. What have you learned about preventing their destructiveness, especially destructiveness to to our economy or to particular populations? How can we better prevent destructive floods, even though sometimes floods are going to happen?
That question, has many different ways. There's a lot of things that could be done.
Mm-hmm.
Of course, the one thing that I think is important is that we can better understand how floods work and operate and what their sizes might be. Then we can be better prepared for mitigating the consequences of floods.
So maybe better understanding of the risks in particular locations.
Yeah, exactly. And the risks. There's quite an established protocol for trying to minimize the damage of floods in urban areas through Floodplain Management Act, floodplain management ordinances, the flood insurance program, and that sort of thing. There's the policies and politics, of course, are very complicated. One angle that has interested me for a long time is trying to figure out ways of better understanding the frequency of large floods. And one way we've been working, one thing we've been doing to work on that is to use the geologic record of floods to better understand flood frequency. For example, most floodplain management ordinances are focused on the so-called 100-year flood. That's the flood that has a 1% chance of occurring in a given year. But to really know what the magnitude of that flood is, you need to have a pretty long record of floods for a given site. In some places, we do have 100 years of flood records, and with a record that long, we can have a pretty good idea of what the 1% flood chance is. But in a lot of places, we don't have that type of record. And then in some places, for certain situations, we really want to know what the chances are of even larger and rarer floods, like the so-called 1,000-year flood or the 10,000-year flood. Critical structures like nuclear power facilities that are located along rivers. We don't, a 1% chance of those being inundated is too great.
Right.
So so in those situations, geologic record, in some places can be really helpful figuring that out. And we've been working on that question in a few places around the country.
Well, it's just about time for us to close, but maybe you do field work for a lot of your research, right?
I do. It really keeps me.
Yeah.
That's my favorite part for sure.
Yeah. So tell me a little bit about what you love about field work, what you like doing outside, and we'll close with just some good field work stories or field work love.
Yeah. I'm hugely fortunate to mainly work in the western U.S. Pacific Northwest, where there's just an incredible diversity of landscapes, beautiful landscapes, but also a great diversity of rivers. And I guess for me, what is that it never ceases to amaze me. Every river I work on, every place I work has, there's some similarities in the stories, but there's always something different that we learn. And it's not something that you can just sit back and model on your computer.
You have to experience it.
Yeah, exactly. And it's those experiences where you discover new processes that you didn't really think about, and how they affect rivers and floods. Floods has been one of those. In the last 50 years, we've learned more and more about how important floods are to shaping many river valleys, and floods generated by different processes, landslides, debris flows, by ice dams, by floods breaking out of volcanic calderas. It's just an amazing suite of processes out there. So I'm not sure I really answered your question there, but it's those types of things that really keep me going.
Yeah. Well, are there any other questions that I didn't ask you that you wish I had asked you? Did I do a good job?
No, I can't think of any. So.
Okay. Well, thank you so much for joining us and telling us about your work, and good luck with it.